discussing two types of secondary structures in biological systems. What are they? No, that's not secondary structure. It's alpha helix and beta sheet. Okay, that's secondary structure. This and this. Okay, alpha helix. Beta sheet. These are both secondary structure. Both of these are made up of amino acids. What links amino acids together? Amide bonds. And amide bonds have this is the building block. Okay? How much energy do I need to break this bond? Joule. 100 kVt. Okay, so several EV. You guys are very strong bonds. How much energy do you think I need to uncoil this helix? Less or more than 100? Less. Okay. So probably some fraction of 100 kVt. So to break this, to uncoil this, probably 20 to 30 kVt. Why? Because these are held together by weaker electrostatic interactions. Okay? Okay, so this is what we've been, basically in the last 3 or 4 lectures, this is what we've been talking about. So, what makes the amide bond or the special or unique? They are atoms with different electronegativities. This gives a partial minus here, partial positive here, partial positive here, partial minus here. And this leads to bonded dipoles that then gives the total amide bond a macroscopic, a dipole of the backbone. Okay, so it has a large dipole moment. And one of the unique things about the amide bond is that it's characterized by resonance, which means that the double bond can fluctuate between the CO and the CN. And this has to do with specific hybridization. So there are p orbitals sticking out of the plane, and when the p orbitals overlap, they create pi delocalized electron systems. And that's what's going on here. Okay, so that was just the review of what we've been discussing. And then we went on to say, well, if I want to distinguish between alpha helices and beta sheets, I need to have some sort of order parameter to distinguish between them. And the typical way of doing that is by using these dihedral angles. Okay, so these are 2 dihedral angles, phi and psi, that are essentially built on looking at planes of 3 atoms. So one looks at that plane, and looks at the angle between the surface normals, and that angle between the surface normals is the dihedral angle. If you do a probability distribution or a histogram of all the phis and psis of all the solved protein structures in the database, because there's a database of solved protein structures, what you get is something that looks like this. This is known as the Ramachandran plot. And so, by looking at phi and psi, I can, for the most part, distinguish between alpha helical structures and beta sheets. Okay, and this you'll see as we start in this class, as we start dissecting what builds up the structure, why this is the case. Why is there, well, if you would look at this picture, what observation would you make, apart from the fact that they are two, let's say, populations, or two peaks? What's interesting about the plot? What else is interesting about the plot?
Localized.
It's localized on one side. You don't have anything on this side. Okay, well then the natural question is, why? Why is there only certain phase and size that are allowed? Okay, so now we're going to try and sort of build on that question. But so this was just a review of what we talked about in the last couple of lectures. Okay, so to understand why there are certain phase and size that are allowed and others that aren't, you have to go back to your chemistry and remember something known as trans and cis isomers. Okay, so peptide backbones. This is the Amide Bond, CONH. This is how we've been drawing it, right? We're drawing the CO pointing up and the NH pointing down. Okay, but the peptide backbone can also exist in two different isomers. It can exist in a trans isomer, which looks like this, so the NH and the CO bond dipoles point in the opposite direction, or you can rotate about this bond and you can get a cis isomer, where the NH and the CO are pointing in the same direction. So these are known as trans and cis. It turns out, and for reasons that we understand, that trans is more stable than cis. Why? Well, when I take, let's go back here. So remember, there was a reason why the different side chains, R1, R2, R3, are all orienting in more or less in opposite direction. This is because you have trans as the dominant isomer. Okay, so as a dominant state. In cis, when the NH and the CO are both pointing in the same direction, the side chains, the R groups, are very close to each other. And what this means is that you have steric clashes. So because of essentially Pauli repulsion, it costs a lot of energy to put these two groups that are usually big side chains close to each other. So it's very high up in energy, it's not going to be stable. Okay, and this is one of the reasons why, or the main reason why, this region is basically essentially not populated on the Ramachandran plot. Okay, it's because trans isomer is much more stable than the cis isomer. If you want to have a simple, let's say, if you don't like the language of isomer, think of them as two states. Okay, I have two states, one is much lower in energy than the other. That's all it is. And then, of course, when you do the Boltzmann weight of these things, this ends up being much lower in free energy compared to the cis isomer, or the cis state. Now, this, with the knowledge of this, you should be able to explain why, when you see a picture like this or a diagram like this, the R groups point in opposite directions. So it's not just a cartoon. There's a physical reason why they're drawn in that way. Okay, so I expect you to be able to know and understand why that's the case. Okay. So this basically summarizes what I've just said, but so are there questions before I move on? Okay.
What are those green atoms again? What do those represent? Are those the
These
orange?
guys?
Yes.
Carbon.
Carbon.
Carbon. Because this is carbon, oxygens.
I mean the green one.
The
Because
green.
they're pointing in different directions.
Uh,
the R groups.
So I'm colorblind, so you have to tell me well, which atom?
Stop.
Stop? Okay. This is the side chain.
Okay, so
It's the R group.
R group. They're pointing in different directions.
They're pointing in opposite directions. They're pointing in opposite directions because of the fact that trans is more stable than cis. Okay? So again, I remind you that the R group is the thing that can take on different chemistries. Okay, every side chain has different R groups. And these R groups are made up of all these different types of chemistry. Okay. Good. So now let's dissect a bit more this alpha helical structure. So the alpha helical structure is represented as this coil, but you have to keep in mind that this alpha helical structure is made up of amino acids, and the amino acids are made up of NH and CO bonds. That must mean that if I coil the helix into this type of structure, those interactions must be stabilized somehow. Okay, because, so let's, I have a CO group here, I have an H, and then somewhere else here I'll have maybe a CO, and then an NH, and then maybe another CO, an H. Okay, so now I'm drawing it without, this is incorrect actually, the way I'm drawing these groups. Okay, so apart from this one here where they're nearest neighbors, all these other ones, except for this other one is incorrect. Okay, so this one is obvious. This is the amide bond. There are several of these amide bonds. So how do various amide bonds talk to each other? And that's the question. And that's what determines what stabilizes an alpha helix. Okay, so let's look at that more carefully. So, if you were to look in detail at the alpha helix, remember I told you that each amide bond has a dipole. Okay, and so what comes out of this is that in an alpha helix, all the local dipoles of the amide bond build up into a macroscopic dipole that all point in the same direction. And so this is one of the things that stabilizes the alpha helix. So that's one point. The other point is that there must be something stabilizing the interactions between different amide bonds. And you can sort of see this here. Let's take this example here. So let's look at this NH bond. This is an NH bond from one amide dipole, and you see it's coiling up, coiling up, coiling up, and then it's interacting with the CO of an amide dipole that's further down the line. Okay, and so in an alpha helix, the nth residue, the nth amino acid, the nth amide dipole forms a hydrogen bond or an interaction with the N+3 or the N+4 amino acid in the sequence. Okay, so I have a sequence of amino acids, A, T, L, E, P, K, G, etc. Remember, these are symbols for the different amino acids. This thing will coil up, and when it coils up, on average, this forms interactions with that, this forms interactions with that, this forms interactions with that. Okay, so you don't have an interaction between, you don't have an electrostatic interaction between the nearest neighbor in the sequence, but you have an electrostatic interaction with the neighbor that's 3 or 4 elements away on average, depending, of course, on the extent of the coil. That doesn't mean that the nearest neighbors do interact. They do. They have covalent bonds between them. Okay? So, well, let's think of it. So if I had a so I take 2 sequences of amino acids, A, K, G, A, K, K, L, okay, so I have 3 sequences of amino acids. This is made up of 3 amino acids, 4 and 6. Knowing what I just told you, we should be able to say something about the stability of forming an alpha helix, alpha helical structure in these 3 different sequences. So, can an alpha helix form in all the 3 sequences?
No.
No.
4 and 6 is not allowed.
Which one?
4 and 6.
You say this is not allowed.
Yeah, but you said that there is no electrostatic interaction between the nearest neighbor.
No, but that's true. But so remember, these are. Let me put this here. They're covalent bonds here. So, I know you missed the lecture. so all of these are covalently linked together. Okay, so they're stuck to each other. You can't do anything about that. Okay, so there's some covalent interaction here that keeps them stuck. So now I have to think about something else. So that's not true. Okay, so it's not true that the only 4 and 6 would not be able to form alpha helices. So which ones would? Knowing this. Probably 6 would be the most stable. This one, I can do that. And then, okay, no happy interaction there. And for sure, here, okay, so the minimal size of a protein amino acid sequence that I need to stabilize an alpha helical secondary structure would be at least 4 to 5 amino acids, at the very least.
But okay, so the first one can interact with the last one, but is there some kind of a boundary condition? Because the second one,
well, in which one?
like in, let's say 2.
2, yes.
So you said that this is the minimum. Or are you going to repeat it again?
No. So here I'm saying this is the whole amino acid.
Okay.
This is the whole protein.
Okay.
It's only made up of 4 amino acids. It's not It's not repeated.
So if that is the case,
Yeah.
so for stability, is it enough just to make like one interaction? Because
Good.
in two,
Yeah.
like A will interact with L, but what will the K and K will do?
Absolutely. So you're right. It will not be as stable, but so okay. We haven't got there yet. Right now, we're just thinking about interactions within the amino acid. But remember that there are also interactions with the liquid around the bath. And so, in this case, you could form an interaction with, you could stabilize transiently something that will look alpha helical. But you're right, it's not, it would not be a stable alpha helix.
Just one
Yeah.
question. So while saying that it's like N plus 4 residue away,
Yes.
it's because of the packing, right?
It's because of the coil.
Coiling.
Yeah.
So can't we have a kind of a different kind of coiling and
Yes.
make it interact A to Z, like let's say.
Can you have?
For example, if the coiling is long, then okay,
Yes. Ah.
in the middle there are other stuff.
So
Tighter coiling.
So this would be something, let's say something else. So let's say you could have something like this, for example. You could also have something like this, but it would not be coiled in an alpha helical way and in the way that is given by when you compare with a reference distribution.
Okay, yes.
Okay, so I have a reference.
Okay, the structure is the constraint lens.
Let's say, okay. Okay, so what else? So let's say roughly. So to give you a sense of the length scales here, the diameter of this object here is about 4 to 5 angstroms. Okay, that's how wide it is, and roughly. The pitch, so the amount of how high along the axis, the height of the cylinder you move will be given by about, it's 1.5 angstroms per every 100-degree rotation. Okay, so and this is again given by the restrictions of the hydrogen bonds. So then you can sort of figure this out, because you can estimate what the length of this hydrogen bond is roughly. So this length between this oxygen and this nitrogen is about probably under 3 angstroms or so. Okay. So that is just to give you a sense of the length scales associated with this. And the number of residues for every turn is about 3 to 4. Okay? So that's what characterizes a helix, a helical structure, an alpha helical structure. Okay, so I mentioned this before, the bond dipoles, the Amide Bond dipoles in an alpha helix all point in the same direction. So this gives a macroscopic dipole, and what this means is that you can think of it as there's some surface charge at the top here of the helix that's positive, and surface charge here at the bottom that's negative. Why is that important? Well, now this helix is going to be interacting with lots of neighbors. Okay, and so the extent of this surface charge can stabilize either negative or positive groups, depending on the particular needs of the protein. So that's one point. So for example, you see, if you look at a protein structure, you see an alpha helix, and you happen to find some positively charged residues around this end of the helix. Well, that should not be surprising. Okay, I see some negatively charged residues here around the one end of the alpha helix. That should not be surprising. So nature has designed these things over millions of years to optimize all these interactions in a very efficient way. Okay? And it's for a particular function. So, what kind of function? So, if you look at the geometry or the structure of the helix, now this is looking down into the center, and okay, so there's your amino acids coiling down. What do you see? Well, the side chains are packed out around the helix in different directions. And what is often used for alpha helices is that they can be amphiphilic. What does that mean? They can stabilize polar interactions and non-polar interactions. Okay, so they're, again, they have a bisexual behavior. So on this side, for example, the side chains here may be non-polar. Okay? And on this side, they may be polar. So this allows, you can use this building block, this architecture, to stabilize in one building block an interaction where the solvation free energy would be large and positive on the left side, and on the right side, stabilize polar interactions where the solvation energy, free energy, would be negative. Okay? So this would allow for diversifying many functional interactions in, for example, the membrane of a protein, of a cell. Okay? So this is just one example of how a helix, because of its architecture, because of the way the side chains pack around it, you can design something to have different chemical groups on different sides, which would diversify its functionality and its interaction. Okay, so that's alpha helices. Let me see. Maybe I'll show you this now, just to. So that it becomes more practical. Let's see. Here. Okay, so let me also do the following. So this is a real structure from an experiment, okay? So you can use X-ray crystallography or electron diffraction. You did electron diffraction, right? No. No, who did electron diffraction? Someone talked about electron diffraction, right? No, okay, never mind. Okay, you can use X-ray, electron diffraction, NMR to solve for the positions of the particles. Okay, so this is an example of a protein which has 3 helices. Okay, and what can you, based on our discussions that we've had up to now, what are the things that stand out to you? So I'm going to just rotate a bit so you can. So I'm going to just put some So again, the color codes are oxygen is red, carbon is gray, and blue is nitrogen. Okay? In the protein. These guys here are water, crystallographic waters. So when you do an X-ray experiment, you're doing these at very low temperature, and so sometimes water molecules get trapped in the structure. Of course, all these proteins they function in a liquid environment. Okay. Let's look here at the backbone. So remember we discussed the bonded dipole. Okay, so this is the CO group, and there's a nitrogen here, but what's missing? So I have something that looks like this. So these two are here. But what's missing here?
NH, the bonds.
The NH. This is not here. It's not in the structure. Why? You were going to ask me. Why? Why is it not there? Okay, so now I'm asking you why. So let's say I'm doing X-ray. I'm doing an X-ray spectroscopy experiment. Who did X-ray? Who? Okay, tell me why I don't see, where's this? Can I resolve the positions of hydrogens with X-ray?
It's too light.
Is it a question of lightness?
Light means it doesn't provide enough.
It's about the cross section.
Yeah.
Yeah, exactly. So it doesn't provide enough cross-section to scatter.
Yeah. So is it actually? It's basically weight, because higher the weight, generally.
Yeah,
It's the
no, sure. Of course it's correlated, yes. So that's the reason why. So you don't see it here because I'm doing an X-ray experiment and I don't resolve the hydrogens. But of course they're there. The hydrogens are there. They're just not seen in the experiment. So I need to go in and put the hydrogens there. Yeah, but this can be done. This can be done. You can, how would you do it? Well, you could do a Monte Carlo, for example. I would say I'm going to take hydrogen, insert the hydrogen in various positions and do a Monte Carlo in Metropolis until I go low down in energy, and it will find its equilibrium position, which will be more or less the one that stabilizes the hydrogen bond. That's
The task is very difficult.
why?
I mean, if you are forming side chains, you need to do
Why is that?
you basically you want to put in one by one initial sites.
Okay, so it's difficult if you would do it in a random way. Okay, but now of course the position of the hydrogen cannot be. So if let's say if my proposal is that the hydrogen is somewhere in this vicinity. Okay, so then it's a question of I build a grid, a dense grid, and I try insertion positions only in this region. Okay, and if I localize it to some region of the phase space, it's not difficult actually to do.
And also one thing,
Yeah.
I think around the loop,
Yeah.
there is this sequence.
Yes.
So if we do it for one pocket, I think
Yeah.
that can be repeated in the other, or is it not?
They may not be symmetries that are preserved across the different because remember they're not the same amino acids.
Oh yeah.
They're different ones. They could be the same, but not necessarily. And also imagine that this is it's one snapshot of the configuration taken at 100 Kelvin. So there'll be some thermal, distortions that will cause asymmetries. But regardless, this is not difficult to do.
Machine power.
What?
We that configuration of the machine we don't have a machine power.
No, you can do it on your laptop. Yes. Seriously, you can try it. Okay, so that's one thing. What else? Can let me move this up. What else? Is there anything else here that comes to your attention? So let me give you a hint. So think about the R groups that we discussed. Is there anything particular about R groups that are outside versus R groups that are inside? Okay, so this is an R group. Okay, this is an R group. It's a side chain. Let me highlight it. Let me try and highlight this more clearly so you can see it. Res name. No. Okay. So now I have highlighted a side chain which has a negative charge, CO minus. Okay? So there's one amino acid that has this group. It's a negative charge. And what do you see? Then the negative charge tends to be pointing, it's hanging outward. Why? Because you've got the liquid out there. Okay, so there's no liquid shown in this diagram, but of course you have to imagine that this is in a liquid. Okay, so that stabilizes the interactions of the negative charge with the outside. But if I look at these groups here, these are my hydrophobic groups. This one here. Okay, let me I'll try and highlight it for you again so you can see it more clearly. Okay, so that's U. So let's hide that now. Let's do U. Okay, there you go. Look at that. This is leucine. Leucine is something that looks like it has oily methane kind of stuff that hates water. It's hydrocarbon. What does biology do? It puts them all together in the center so all the oily stuff sticks together. Why? Because if you put it down here, there'll be a penalty. There'll be an energetic penalty to put these guys outside. So you see that there's, in these biological systems, starting from the DNA and how the protein is engineered at the sequence level, that gets translated into some three-dimensional structure where the original positioning of the proteins of the amino acid sequence led to a situation where you would create thermodynamically favorable conditions for polar things to be interacting with water and non-polar things to be sticking together. Okay, so it's really impressive how biological systems have been designed to do this. And these are very delicate. So if you mutate, you change one amino acid here, this will shift the equilibrium so that it'll make the protein very unstable. Okay? Okay, questions about this before I move to beta sheets? So what stabilizes these interactions in the core? What type of interactions are they in the center here? I've got oily things like this. So if I bring lots of oily things together, what? No? Do you see any electrostatics here? Here. So? Van der Waals packing. That's what stabilizes all these oily things together in the process. Yeah.
Can we once see it from the...
You want to? Yeah,
this?
sure. Like this?
Yeah.
Yeah, sure. So there's a channel in between.
I was just trying to compare it with the one that you showed before, 7 and 9, 10. From the same view.
No, say it again.
It was in one of your slides, this view.
Ah, was it?
You just saw there.
That one. Yeah. This is the sort of like the inverse. In the sense, so there it's one helix.
Yeah, one.
Now we're at 3. And so in the one helix, you had functionality to stabilize polar, non-polar, one helix. In this one, by bringing 3 helices together, for another function, I put all the non-polar things in the center and all the polar stuff around me. So this is the type of thing where 3 helices would have to survive in solution. So in a symmetric environment.
Regarding this stability of polar and non-polar thing,
Yeah.
is the number of helix that forms a group. Is it 3 or it can change?
It can change. It can change. So you can have helix bundles of different sizes. I don't know exactly if there's any relationship between, the numbers of in the helix bundle and stability. It's a good question. I don't know. It could be. Could be. Yeah.
What is in the cup? Just air?
What do you mean? Air? No.
Like maybe in the gas, like the hydrogen. Okay, should we suppose that maybe that's where the hydrogen may be?
No. Wait. So wait. These are. So this is a protein. It's made up of carbon, oxygen, nitrogen atoms. Okay. When you pack these things together, there will be empty spaces because of it's not perfect packing. Okay. So now your question is relevant if you start thinking about other proteins like myoglobin. So myoglobin is a protein that binds strongly to oxygen. It's the thing that binds to oxygen and releases oxygen. Okay? So gas molecules in the liquid, which is mostly water, will bind to, not this protein in particular, but other proteins. And certainly the size of the amount of available empty space will be important for controlling how strongly the gas molecules bind to the protein. Okay, but that's another topic altogether.
You said that this was, the positions of the atoms were obtained from experiment.
Yes.
It was reconstructed numerically.
The positions of the atoms shown here are experimentally resolved, and then if you want to resolve the protons, then they're done numerically. Because with X-ray crystallography, you cannot resolve the positions of the protons. So you need to have some numerical techniques to be able to do that. Okay, so let's move on to the beta sheet. Joe, you have a question? No, ask. Don't be shy. Okay, so alpha helix, check. Now, the other secondary structure that is relevant in biological systems are beta sheets. So they're typically drawn like this, and this is how they look. So these are very different from the alpha helix. The alpha helix, they coil. So these will interact with amide bonds along the chain in the alpha helix. So here it's N interacts with N plus 4. And it's plus, I put this in quotes because it's about 3.5 to 4. Okay? Over here, this is not what happens. Over here, what happens is you get situations where two beta sheets will interact in this way. Okay, so they form like a zipper. Okay, so I have a sheet and a sheet, and they can align, sort of stack on top of each other like two graphene plates. Okay, instead of just being interacted with van der Waals interactions. Now they have these bond dipoles that interact this way. Okay? And this is shown pictorially here. Okay, so this is a beta sheet. They can be classified in parallel and anti-parallel conformation. Parallel and anti-parallel comes from the fact that, remember, the ends of, not the ends of a helix, but the ends of any peptide sequence, remember, have termini groups. The N terminus and the C terminus. It's negative, positive, negative, positive. And so this is like two anti-parallel dipoles. Okay? And if this is the other way around, then you have parallel dipoles. And so in the beta sheet, you have hydrogen bonds that form across different strands. And they try to form hydrogen bonds that are linear. Okay? But they may not be commensurate. Sometimes there might be defects. So this will misalign the hydrogen bonds. Okay? So the beta sheet is, in some sense, quote-unquote simpler in terms of its morphology. Okay, the only thing to remember is that it has, it can be in a parallel or anti-parallel conformation. And in beta sheets, the interactions have nothing to do with where they are nearest neighbors in the sequence. Nothing to do with that. This can be forming, they will form interactions with a different chain altogether, for example. It doesn't have to be a different chain, but for our discussions right now, let's imagine that we don't have these two being connected. Okay, so for now, these are not connected. They can be. Okay, so an example of, like I gave you for the alpha helix, of the beta sheets being used for a particular function is the following. So beta sheets are good at creating baskets. So this is a nano basket, and it's a nano basket because of the way you can essentially form these nets around a molecule. And this is an example of a situation where you have a molecule that looks like this. It's hydrophobic, doesn't like water because it's only made up of oily hydrocarbon stuff. And by creating a beta sheet basket like this, you point all the hydrophobic groups into the center, and this stabilizes the oily retinol inside it. So again, in both this example and the example of the alpha helix, what you should take home away from this is that the amino acids with different chemical groups build up into secondary structure, and then their different polarities allow them to create three-dimensional architectures that then allow for stabilizing molecules of different chemistries in different environments. That's what essentially is going on. Now, again, we mentioned this before, but in all these pictures, we're typically neglecting, we're throwing away all the environment in our description of this, our representation. But we're going to come back to, maybe in the next class, of trying to understand what the role of the solvent is in stabilizing these types of interactions. Okay, I think I'll skip this. Let's see. Should I go on to something? Yes. Yeah, so let's move on to, since we've been talking about this a lot, so the relevant molecular interactions and the length scales that are associated with that. Okay, so We've discussed this at length. Covalent bonds, very strong and very difficult to break, and very strong. This maintains essentially the essential architecture of the organic molecules. There are other types of covalent-like bonds known as disulfide bonds. So these are covalent bonds that form between sulfur atoms. Okay, we'll talk about this shortly, but they are weaker in strength. And so typically the length of the covalent bond is correlated with how strong it is. Shorter, stronger. One of the things that biology uses a lot is electrostatic interactions, and electrostatic interactions with different amounts of screening. So this is a sort of a typical electrostatic interaction in proteins. The minus charge that we saw already with a positive charge. And this is an electrostatic interaction, goes as 1 over r, it's long range. But the range of it and the strength of it can be sensitively tuned by the medium. And so the dielectric constant, let's assume that that's a reasonable argument to invoke, will change the length scale of the interaction and also how strong the interaction is. So how would we think about, what could we do to think about what the strength and the range of the electrostatic interaction is relative to thermal energy? So I have electrostatic interaction. So remember, kBt sets our energy scale, because that's always the starting point. So I have kBt. Okay, this is about 25 millieV. Okay, now I have an interaction between two charges, and this goes as okay. Now, I know that this interaction goes as 1 over r epsilon. The magnitude of the epsilon will affect the range of the interaction, the strength of the interaction. At what length do I need to be to start worrying about how this energy, and let's call this Coulomb, and this is thermal. So at what length do I need to be to start worrying about Coulomb versus thermal? Okay, so another way to ask this question is the following. How does kBt compare with that guy there? So I have two charges. Let's start in. Let's ignore epsilon first of all. Okay. How would I go about thinking about this problem?
Very, very less distance.
At very, very, okay, that's a good start, yes. So, very, very less distance. Okay. And how very less?
Less than nuclear distances.
Less than nuclear distance.
That's like inside it, like less than angstroms.
Are you sure? So how did you come up with that?
Okay.
Yes.
So,
Sorry. I think I've taken that in the wrong units. Sorry.
okay, wait. And the other guys, wait. Do you understand the question first? Okay, so I want to know basically at what length I should start worrying about this energy compared to thermal energy. At what length does this get larger than this?
After 10 to the 9.
So you might be right, but you're right for the wrong reasons. So don't look at that plot yet.
That's what I expected.
Why do you expect it?
Because we know that at 10 to the 9,
10 to the minus 7.
scales tend to convert, and after that,
So this is it again?
I'm saying at 10 to the okay, at the nano scale.
Yes.
All energies tend to converge to you. But after that, or away from that, we expect.
Okay. Fine. But
No,
Okay.
we just equate it and
Yeah.
give the value of electrons like 10 to the minus 19 square and
Exactly.
equal that. So we'll just
exactly. That's it.
I didn't realize I was using RN meters, so it came.
Okay. So basically, I have this, and this is in energy. These are units of energy. I have this in units of energy, so I can define the R star, which makes this equal to this. Simple. And you will get what you're saying, more or less. But now you know where it comes from the point of view of the electrostatics. So just imagine, sodium chloride in water. You dissolve it in water, you mix it, and now the sodium and chloride ions are undergoing free diffusion. What type of effective potential do the two ions feel? Well, when they're far away, the potential will be flat. They don't see each other. But then, rarely driven by just diffusion limited process, they will come close, and when they come close, something will happen where the magnitude of this energy will get much larger than thermal energy, because when it's far away, it's just thermal fluctuations that are making it move around. When they come close, at some length, they will feel a very strong interaction, and that's when things get interesting and where one has to worry about the explicit role of electrostatics. Okay, it turns out that you can do the math yourself, that length is about 7 angstroms. So this R star equals 7 angstroms, roughly. Of course, depends on the details of the epsilon. Okay. But if you choose epsilon equals 80 for water, this is what you'll get. Now, it also assumes that I can invoke something like a dielectric constant. Can I?
What is the question?
So this argument of where I get the 7 angstroms assumes that I'm neglecting correlations in the liquid. So the epsilon, this epsilon is not constant also.
Like
Right.
varies.
The epsilon may and will have some R dependence on it. Okay, fine. So you could put in a distance-dependent epsilon, well, what effect would that have? Probably, as it will vary, and as the ions get close, as two charges get close together, the dipoles in between get polarized, and so the permittivity, the relative permittivity will slightly reduce. Okay, and so instead of having an epsilon that's 80 as a function of r, it may be something like this. I don't know exactly. I'm just kind of making this up. So it may drop. Okay, fine. As long as it doesn't drop to epsilon of a non-polar object like oil, it may go down to maybe 75, but okay. So this length may increase a bit. Okay, fine. But effectively, that's where again we're at the nanometer length scale where electrostatic energy can get much larger than thermal energy, and then that can be very, very important. Okay? Now this doesn't mean it doesn't contradict what we talked about earlier about the convergence of energies and forces. It's also reinforcing that point that thermal fluctuations at these length scales can modulate efficient conversion into different forms of electrostatic energy. Or it can convert electrostatic energy into mechanical work at these length scales. Okay, so the two are consistent. Okay, so this is an important thing to keep in mind. So any questions? Joel? Don't be shy. Just ask. You still have fluctuating what? Sure. So, think of this as, so this fixes thermal energy, but there'll be thermal fluctuations. Okay, and thermal fluctuations will couple with modulating how strong or weak the electrostatic energy is at a particular length scale. So I'm giving you here just sort of a static frozen picture, but of course there are fluctuations involved. Okay, so maybe now in the last maybe 10 minutes I just show you some fun stuff. Since it's okay. People with straight hair and curly hair. Okay. Well, the morphology of your hair, whether it's straight or curled, is related to proteins. It's related to the chemistry of the protein. It's related to, so proteins are, hair is essentially made up of fibers, and those fibers are proteins. So everything, almost everything in biological functions happening in you and the surroundings comes from proteins and building blocks. And what makes hair straight versus curly is these sulfur-sulfur bonds. These are known as disulfide bonds. Okay? And so, there are people, well, typically women, who will put chemicals in their hair when they want to make a perm. I think they call it a perm. And they want to make the thing curly. Okay, and so when you make the thing curly, what it does is it breaks the sulfur-sulfur bonds. And by breaking the sulfur-sulfur bonds, things can twist around more easily, and then you get curly hair. Okay. So we're going to come back to this later on a more serious example, but again, just an example of how these molecular building blocks are at the heart of lots of things that you may not have seen before or not have appreciated before. Another example, which I think is rather interesting, there are these bacteria that can survive in the vents of volcanoes. So at very high temperatures. How do they do that? How does a bacteria survive in a vent where the temperature is of over 100 degrees Celsius? Because if you take if you took our proteins, our cells, to high temperature, they denature. Things break apart. Well, these bacteria have evolved over a long time to survive in these conditions, and because they have evolved to produce proteins with more cysteine. So cysteine is this amino acid which has sulfur. And the way this was discovered was the following. So these are basically distributions of across different bacteria, proteins in bacteria that live in vents versus bacteria that don't live in vents. Okay, so these are the ones that survive high temperature, and these are the ones that don't. And the y-axis is a count, so it's the population of something on the x-axis, which is the number of cysteine residues in the protein. So they look at a class of many different proteins in the bacteria, and they count the number of cysteine residues in ones that survive in bacteria versus ones that don't. And what do you notice? What's the difference between those that survive in vents and those that don't?
What is it x-axis?
X-axis is the number of cysteine residues. So I have a protein, and they count the number of cysteine residues in the protein.
And y-axis
was? The count of the number of proteins with that number of cysteine residues. So y-axis is the number of proteins with, for example, 0 here means there are 180 proteins in the bacteria that survive in those conditions that have 0 cysteine residues. Then there are 60 proteins that have 1 cysteine residue. A 100 or 90 proteins that have 2. Same thing here.
I think the number 2 has something here. So
Aha.
it has a peak.
It has a peak.
So 0, it's same.
The same, exactly, very good.
But 1, it sharply decreases.
Slightly decreases, perfect.
2, there is a sudden.
There's a spike.
Yeah, sudden spike.
So, and if you continue this, you would see that there'll be oscillations. So, even number is peaked compared to those. And this is, this is what triggered off an interest in these proteins, because in order to form these bonds, so these are 2 cysteine residues. The disulfide bond is formed between 2 sulfur groups that come from 2 cysteines. Okay, so a disulfide bond is a covalent bond between 2 sulfur atoms, and in order to form them, you need 2 cysteine residues. So what does this mean? What this means is that in these proteins, usually you would not have two pairs, or a single pair. And usually in a typical protein, two amino acids that are very far away don't have a covalent bond between them. They only have electrostatic interactions, van der Waals interactions. Here what happens? You form strong covalent bonds between different parts of the protein that are not covalently linked. So let me just draw this for you so you have a picture. So normal protein. Okay, well, I can do better now since we know this. Okay, let's say this is a normal protein. So an amino acid here only interacts with an amino acid here by electrostatics and van der Waals, nothing else. Okay, now I go to this, let's call it abnormal or thermophilic. And so this and now I form covalent bonds here, or covalent like. Why? I need to have, what happens if I take this guy and I heat it up to 100 degrees Celsius? It breaks apart, it's going to unfold. Now if I put a covalent bond, I am able to maintain the secondary structure. I'm able to inject thermal energy into it to rather high temperatures and still maintain its structure. And if I maintain its structure, it can perform its function. Okay, so this using, a mixture, a variety of molecular types of interactions, you can generate, you can respond in an evolutionary way to stimuli and generate all sorts of architectures that can survive under different conditions, which is sort of interesting. Okay, I think we'll stop for today. See you, so not on Tuesday, because I'm not here next Tuesday, and actually not on Thursday either, because I'm not here on Thursday. So we're going to have to